How do you travel from one place to another? Do you walk, ride a bike, drive a car, take public transportation, fly? Regardless of how you travel, you are utilizing kinetic energy, which is the energy of movement. If you walk, you are also utilizing the potential energy stored in the bonds of ATP to allow your muscle cells to contract. If you drive a car, the gasoline fuel has potential energy in its chemical bonds that can be utilized to move your car. This section discusses different types of energy and energy conversions. Energy is the capacity to do work. An example of work in your cells would be building molecules. An example of work for your body would be moving a heavy object, which requires you to exert force. There are two types of energy, kinetic and potential. Kinetic energy is the energy of movement. Examples of kinetic energy include heat, which is the movement of molecules, and walking or driving a car, as mentioned at the beginning of this lecture. Potential energy is stored energy, meaning that it has the potential to be used to do work. Examples of potential energy include the chemical energy stored in the bonds of the molecule ATP. Another example is the electrical energy stored in a battery, which can be used to power an electronic device. The molecules in gasoline, known as octane, which shows the chemical formula here, contain potential chemical energy within the chemical bonds. This energy is transformed into kinetic energy that allows a car to race on a racetrack. Thermodynamics is the branch of chemistry that studies energy changes. There are two laws of thermodynamics. The first law is the law of conservation of energy. This states that energy can neither be created nor destroyed, which means that the total amount of energy in the universe remains constant. However, energy can change forms. We go back to our example of driving a car. A car converts the potential chemical energy of gasoline into the kinetic energy of movement and heat. Here we see many energy conversions which will keep the amount of energy in the universe constant. Most life forms on Earth get their energy from the sun. Plants use photosynthesis to capture sunlight, and herbivores eat those plants to obtain energy. Carnivores eat the herbivores, and decomposers digest plant and animal matter. Organisms also radiate heat energy back into the atmosphere. Here we see two more examples of energy conversions. Energy being transferred from one system to another and transformed from one form to another. Humans can convert the chemical energy in food, like this ice cream cone, into kinetic energy, the energy of movement to ride a bicycle. Plants can convert electromagnetic radiation, which is light energy from the sun, into chemical energy. The second law of thermodynamics states that energy tends to be converted from more useful to less useful forms. Let's go back to our example of driving a car. When a car engine burns gasoline, the chemical energy of gasoline is converted into kinetic and heat energy. The kinetic energy that moves the car is useful. However, the heat energy that heats the engine, the exhaust system, the tires, the air, and the pavement is non-useful. The heat energy goes off into the atmosphere and does nothing to drive the car. Processes that proceed spontaneously, which means that once they start, they go to completion, lead to increasing randomness and disorder called entropy. Entropy can only be overcome by adding energy. Examples of entropy are the following. For example, the ordered carbon molecules in liquid gasoline become disordered when gasoline is burned to create carbon dioxide gas. And what about your house? How easy is it for your house to become messy? Dirty laundry can pile up on the floor, dirty dishes can pile up in the sink, mail and other papers can pile up on your desk, but how much energy is required to actually clean all of those messes up? Entropy is a measure of randomness or disorder in a system. Gases have higher entropy than liquids, and liquids have higher entropy than solids. How can life on Earth exist given the second law of thermodynamics? In other words, where does more energy come from to replenish all of the energy lost to less useful forms? Well, the answer is from the sun. Living organisms utilize solar energy from the sun to construct complex molecules and maintain orderly structures. In other words, living organisms use the energy from the sun to combat entropy. Nuclear reactions from the sun provide solar energy for all of the organisms on Earth. Energy conversions in our cells take place during chemical reactions. The sum total of all chemical reactions that take place in a cell is referred to as metabolism. We typically think about metabolism from a dietary standpoint, such as somebody has a fast or slow metabolism. This is actually true. All chemical reactions in our cells do go back to the diet because when we eat food, we digest that food into nutrients that our cells convert during chemical reactions into the products that they need. Chemical reactions convert one set of chemicals into another set. The chemicals that you start with are called reactants, which are converted into products. There are two types of chemical reactions, exergonic and endergonic. Exergonic reactions release energy so that the products contain less energy than the reactants. You can remember exit, meaning that energy exits during the chemical reaction. Endergonic reactions require a net input of energy from an outside source so that the products contain more energy than the reactants. You can remember enter, meaning that energy needs to enter during the chemical reaction in order for it to proceed. An example of an exergonic reaction is glucose metabolism. During glucose metabolism, glucose is broken down to carbon dioxide and water to extract the potential energy in the chemical bonds. The products of carbon dioxide and water certainly have less energy than the starting glucose molecule. The extra energy is released as heat. No energy conversion is 100% efficient, and energy is always lost as heat. We start with an ordered glucose molecule that is converted to less ordered carbon dioxide and water molecules, meaning that entropy increases and therefore energy is released. Breaking molecules always releases energy. You can think about this as a downhill reaction from high to low energy, like rolling a boulder down a hill. Once you push a boulder down a hill, it will continue rolling until it reaches the bottom of the hill. No further energy input is required to get it to keep rolling down the hill. An example of an endergonic reaction is glucose production via photosynthesis. In this case, plants utilize the starting materials of carbon dioxide and water to produce glucose. Certainly the product of glucose has more energy than the starting reactants of carbon dioxide and water. Therefore, this requires an overall input of energy from the sun. In this case, we are taking less ordered carbon dioxide and water molecules and converting them to an ordered glucose molecule. Therefore, entropy decreases and energy is needed. Building molecules always requires energy. You can think about this as an uphill reaction from low to high energy, like pushing a boulder up a hill. In order to push a boulder from the bottom to the top of a hill, you will need to continue inputting energy until it reaches the top. As soon as you stop pushing the boulder, it will roll back down the hill. Just like if the sun stops expending sunlight, photosynthesis will no longer take place. Building molecules requires energy, making them endergonic reactions, while breaking down molecules releases energy, making those exergonic reactions. Anabolic pathways are those that require energy to synthesize larger molecules, while catabolic pathways are those that generate energy by breaking down larger molecules. Both types of pathways are required for maintaining the cell's energy balance, as we need to digest to break down larger molecules into smaller subunits that our cells then use to build the molecules that they need. I also compare these reactions to building versus tearing down a building. To construct a new building requires time and energy to meticulously put together the starting materials, one brick and board at a time. while tearing down a building is relatively quick and easy with a wrecking ball or other machinery. Here we see exergonic versus endergonic reactions. Exergonic reactions proceed spontaneously to completion once they begin without any further input of energy. This is a downhill reaction as energy is released and the products have less energy, referred to here as Gibbs free energy, than the reactants. Endergonic reactions do not proceed spontaneously and require continuous input of energy to proceed. This is an uphill reaction as energy is required and the products have more energy than the reactants. All chemical reactions, including exergonic ones, require an initial input of energy to get them started. This is known as activation energy, which is the initial energy input needed to perform a chemical reaction. So why do all chemical reactions require activation energy? Well, for two atoms to react, their electron shells must be forced together despite the repulsion between the like negative charges of the electrons. For chemical reactions, the source of activation energy is the kinetic energy of movement as molecules bounce around and bounce into one another. These molecular collisions force electron shells of atoms to interact, resulting in chemical reactions. Molecules also move faster at higher temperatures, so chemical reactions occur more readily with added heat. As mentioned, all reactions, even exergonic ones, require activation energy in order to initiate the reaction. This energy is lower if the reaction is catalyzed, which is a topic discussed in Part B of this lecture. During energy conversions, electrons can carry energy between molecules in oxidation-reduction reactions. Oxidation refers to the molecule that loses an electron, while reduction refers to the molecule that gains the electron. These electrons very often are transported in electron transport chains, which are a series of electron carrier proteins that pass electrons to release energy. These sorts of reactions are important in photosynthesis and cellular respiration, discussed in later units. Common electron carriers include NAD+ and FAD.